All right, in the last few videos, what we've done is we've talked about the separation of charge between two sort of metal plates and how that can give rise to current, the movement of electrons from one place to another. In this video, what we're going to do is we're going to start to develop a model for understanding how those electrons move, how they're related to fundamental quantities that we have that we can measure, and also how they will be related to macroscopic quantities which you can measure in the real world. We'll get to that in the next video. So what I have here is I have a wire that I've zoomed in on, and that wire has these atomic cores, right? A wire is made out of stuff, so there's atoms in it, and those atomic cores make up the material themselves. There's an electric field that is associated with a surface charge gradient that points to the left. So we would expect there to be an electron current that points to the right. That is, that any electrons that we have that are sort of available to move around are going to move from left to right, right? And that is associated with this electric force, which tells us that for negatively charged particles, the force that they feel is opposite the direction of the electric field. So these electrons are going to zoom in here from left to right. Now, what happens is that as these electrons move, they are accelerated, right? If they feel a force, they are going to be accelerated. And so they might start with no velocity and suddenly pick up more and more velocity as they are accelerated. But there's stuff in the way. There's these atomic cores that they run into, they bang into them, they slow down, then they start the process over again, so they start accelerating again. So we can keep track of what their velocities look like as a function of time. And we could say, well, we have one, maybe it starts from rest, and it is accelerated, so it reaches some velocity. And then it runs into a core and it drops down to zero. So it basically loses all of its momentum in that collision because those atomic cores are very large compared to the electrons. And then it does it again. But this time it runs into that atomic core much sooner. There's a closer one that it happens to run into. And we can continue this process, right? Mapping out sort of like different collisions as they occur. And you can see that for some cases, you know, the electron gets pretty far before it runs into an atomic core. In some cases it doesn't, right? And that's going to be a random process for every electron that is in this situation. Now, what we're going to come to find out is that a better model of this, or a way of modeling this, because it's very complicated to track every single electron's motion, is to say, well, on average, these electrons move in a particular way, right? So that is that they have some average velocity that we can model over some amount of time. This is a thing we'll call the drift velocity, but it's also thinking, you can think about it as the average velocity of these electrons. And this model is called the Drude model. It is a sort of foundational model in condensed matter physics. It tells us a little bit about how electrons move in conventional materials. It's also related, in a sense, to the kinds of stuff that you might be used to in chemistry courses or advanced physics courses or advanced engineering courses when you think about averaging over the motion of particles in a gas, right? The sort of Boltzmann distribution and so forth. It's kind of related to that, but instead it's in materials that are sort of conventional. So what we're going to do is we're going to use this idea to make sense of how these particles move, and we're going to develop a mathematical model for this. So what we'll do is we'll start with the fact that we have the momentum principle that tells us about how the momentum changes in response to a force. And so that momentum change is related to the impulse, the force that is applied over a given amount of time. And in this case, it is an electric force. So we're going to deal with electrons that have some electric field that pushes them along over some amount of time. Okay? So in this model, we're going to make the assumption that our electrons start from rest. They are accelerated up to a point, that is, their momentum changes, and then it crashes, right? So what happens is they develop some momentum, but then when they crash, or when they start from rest, right, they are starting from zero momentum. So you can think of it sort of as modeling these 2 points, right? They start from zero and then they achieve some final momentum and then crash. And so that's going to be directly related to the charge of the electron times the electric field times the average time. Now, in these conventional materials, that is metal wires and so forth, these drift velocities are actually pretty small. There's something like 10 to the minus 4, 10 to the minus 5 meters per second. They're slow. And so the momentum in this case is actually just the usual linear momentum. We're not going to expect them to move the way that fundamental particles move, which is really, really fast, right? So we can rewrite this as the mass times the velocity, which is equal to the charge times the electric field times the average time. So what we get is we get a relationship between the velocity, the charge of the electrons and their mass, times the electric field times the amount of time. We're going to make one more model assumption, which is that this tells us about any one of these situations, right? So each of these guys has a delta t associated with it, right? So this is sort of, in a sense, an exact model of this situation. But now we got to average over it because all the electrons are going to do lots of different kinds of things. So what we're going to say is that there's some average time between collisions, which essentially is the average of these intervals, and that average is directly related to the average velocity that those particles develop, right? So what we're making is a model assumption, which is that the average speed that is associated with these particles, these electrons, is going to be related to some sort of average velocity, which you can think of as the average time between collisions. Okay? And so it's this relationship that we're going to exploit to be able to understand how the macroscopic and the microscopic world connect together in the next video. But let's just unpack this real briefly. The average velocity increases as the electron charge increases. That's not really thinking about the electrons themselves, but thinking of them as general charge carriers that have more charge. So the more charge, the bigger the force they feel. That kind of makes sense. The bigger the electric field due to the surface charge gradient, the faster they move. That makes sense. They feel a bigger push, right? As the mass of those charge carriers increases, the average velocity goes down. That also makes sense because they're kind of harder to move, right? It takes more energy, it takes a bigger push to get them to move at the same velocity. So this equation makes sense in sort of our fundamental ideas of pushing and pulling objects around. So to recap, we're modeling the current in a wire as having these electrons that are sort of free to move, but they run into these atomic cores. We average over their collisions to determine an average velocity that is associated with an average collision time. And that gets us this fundamental relationship between the average velocity and the electric field, which is the thing that's going to be important in the next video.